Here's a quick example of binomial probability. Well, let me first sort of say the general formula. At least in one class, we just barely got to the general formula. We'll see if we get further in the other class. But the idea is that if I flip a biased coin n times, and I want to know the probability of getting R heads, let's say. I don't need out of those n trials. Okay. Well, I need to know how biased it is. Okay. So let me just review real quick the example we did before. Let's say this was something where the probability of heads just on one trial, there we go, was 3/4, and the probability of tails on each flip was 1/4. Then what we figured out was we could list all the ways that R heads can come up. Well, that's a standard counting problem. That's going to be n choose, come on, n choose R. It's not coming out real well. But somehow after an equal sign it hates to do that. Let me just see if I can fudge that a little bit. N choose R. There we go. It still doesn't like it much. Oh well. So that's how many ways it can, in the list, we're going to come up with. But then for each one on the list, we figured out, for example, if it was 2 heads and 2 tails, it was 3/4 squared. Well, in this case, it's going to be R. You're going to multiply that by itself for how much probable is the R heads part. But we've also got to keep track of the fact that there's n minus R times it came up tails. And so in general, let's just change this to some number p. And therefore this number is going to be 1 minus p. It's often called abbreviated q. And then this is just going to turn into p. And this is going to turn into q, but I guess I'll just leave it as a 1 minus p. Whoa, hello. That's not what I wanted at all. There we go. Okay, and let me put a little space in here. It's going to look better. Okay, so we're going to have a binomial factor for how many times on the list does this particular possibility show up, and then for each each term in the list, it's going to be this product of probabilities, because it's an independence kind of thing. You've got R independent events coming up with probability P, and n minus R independent events coming up with probability n minus P. So for example, another example would be, suppose that the P, the probability of heads, is just 1/3, so it's actually biased a bit away from heads, and so the probability of tails is going to be 2/3, and I want to know what's the probability of getting 7 heads out of, let's say, 15 tosses. And there's this wonderful formula we've derived. It's pretty nice. P of 7 heads in any order. Remember, this is just the total number being exactly. And let me actually. It's not at least. It's not at most. It's exactly. Probability of getting exactly 7 heads is going to be. We sort of think about. We don't actually do it. We think about, what if I listed all the possible ways of writing out H, H, T, 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 H, H, etc., and with 15 letters, and having 7 of those be the letter H. Well, that's the whole list. And then each one on the list, what's the probability? For example, if it was the probability of, let me just write it out, like suppose it was H, 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 T, 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 T. Okay? So if 7 H's and then 8 heads in 8 tails in that order, the probability is going to be just the probability of each one of those multiplied because they're all independent events. That's really crucial that they're assumed to be independent. And the probability of each of those H's is a third. That's not what I meant to do. And that's going to be times to the 7th. And the probability of each of those T's is going to be a 2/3. And that's going to be to the 8th power. And that's not something, and in order to get the computer to calculate that for us, it likes the other choose notation. It likes this notation. And let's compute it numerically. About 0.115. About a little less than 1 out of 9. 1 out of 9 times you will get exactly 7 heads out of 15 tosses for this biased coin. Whereas probably most likely you'd think to get 5 heads out of 15. In fact, you can show that. We could actually look at all the numbers and see that it actually peaks at 5 heads out of 15 because the probability is 1/3. So that's an example of using this formula. It's a wonderfully powerful formula where if you just know it's in this situation with like repeated independent trials, like flipping a coin, even if they're biased, you can use this formula with the NCR, P to the R, Q to the N minus R, and Q is just an abbreviation for 1 minus P.